Hi children, today I am going to start the next topic, that is the pseudo first order reaction. Pseudo means false. False first order reaction. The order of the reaction sometimes changes by the condition, and the pseudo first order reactions are generally defined as those type of reactions which appears as a second order reaction but behave as a first order reaction. Just for example, during hydrolysis of 0.01 mole of ethyl acetate with 10 mole of water, the various constituents form at time t is equal to 0, and after the completion of the reaction is given as, that is the ethyl acetate CH3COO C2H5. This ethyl acetate take the concentration, that is 0.01 mole, okay, and it undergo hydrolysis with water, and the concentration of water we take, that is 10 mole. After the hydrolysis it give acetic acid, that is a CH3COOH, ethanoic acid, and plus ethanol C2H5OH, okay. At t is equal to 0, initially at t is equal to 0, the concentration of CH3CO C2H5 is 0.01 mole, okay, and the concentration of H2O is 10 mole, whereas the quantity of CH3COH and C2H5OH is formed is 0 mole. At t is equal to 0, no product is formed, so it is 0 mole. At time t, what happens? The ethyl acetate is completely consumed and converted to form the product. That is, the concentration of CH3COO C2H5 ethyl acetate left at time t is 0 mole, whereas the concentration of water left at time t is equal to 9.99 mole, okay, and similarly the product is formed at time t, and the concentration of acetic acid form is 0.01 mole, and also the concentration of ethanol form is 0.01 mole, okay. So during this hydrolysis of ethyl acetate with water, first we take the concentration of ethyl acetate to 0.01 mole, and concentration of water is 10 mole, and after that it forms the product, that is acetic acid and ethanol. At t is equal to 0, when the reaction is starting, the concentration of ethyl acetate remains same, that is 0.01 mole, concentration of water is 10 mole, whereas the concentration of acetic acid and ethanol is 0 mole. After the completion of the reaction, at time t, the concentration of ethyl acetate is completely consumed to form the product, that is, it becomes 0 mole, whereas the concentration of H2O does not alter too much during the course of the reaction, and its concentration changes only to 9.99 mole, okay, and the product form is 0.01 mole, and ethanol also form is 0.01 mole. So students, from seeing this equation, it is a bimolecular reaction, okay, but in this reaction the concentration of H2O does not changes too much during the course of the reaction. So for this reaction, how can we write the rate equation? That is, the rate is equal to, first we write the K star, concentration of ethyl acetate CH3COO C2H5 and the concentration of water. So since the concentration of H2O does not changes too much during the course of the reaction, this term can be taken as constant. So we can write the another rate equation, that is, the rate is equal to K concentration of only ethyl acetate, that is CH3COO C2H5, okay. In this K is equal to K star H2O, because this K star is also a constant term, and this H2O we take the concentration of H2 as a constant because it does not changes too much during the course of the reaction. So it means in this reaction, the reaction which appears as a second order reaction, the reaction which appears as a bimolecular reaction but behave as a second order reaction, that particular reactions are named as the pseudo first order reaction, okay. The reaction the reaction which appears as second order but behave as first order, that reactions are termed as pseudo first order reaction. Okay students, the reaction which appears as second order but behave as a first order reaction, that reactions are termed as the pseudo first order reaction. Another example of the pseudo first order reaction is the inversion of cane sugar. And in the inversion of cane sugar, we know the formula of cane sugar, that is C12H22O11. When it undergo hydrolysis, it give 1 mole of glucose plus 1 mole of fructose. Okay. In this reaction also comes under the pseudo first order reaction, because on seeing this equation it is clear that it is a bimolecular reaction, it is a second order reaction, but since the concentration of H2O does not changes too much during the course of reaction, the rate equation for this reaction is simply written as the concentration of the sucrose C12H22O11. Okay, this is also a pseudo first order reaction. After that we come on the next topic, that is the other methods for calculating the value of the rate constant. In the previous class, we had briefly discussed about that with the help of integrated rate equation, how can we calculate the value of the rate constant or the time required for the completion of the reaction by knowing the concentration of the reactant, that is the initial concentration and final concentration. But when the reaction consisting of the gaseous reactant and the gaseous product, then how can we calculate the value of the rate constant? And here we are using the pressure change method to calculate the rate constant and the order of the reaction. Okay, so the method is the pressure change method. So by using the pressure change method, we can calculate the value of the rate constant for a gaseous first order reaction. So first we take a typical gaseous first order reaction, that is the A, reactant is a gas. On reacting it gives the product, that is B. B is also a gaseous component, and C, the C is also a gaseous component. The integrated rate equation for this reaction can be written as the K is equal to 2.303 by T log Pi divided by Pa. Okay, here this Pi is the initial pressure of A. Okay, and this Pa is the pressure of A at time T. Okay, after the completion of the reaction, this Pa is the pressure of A at time T. Okay students, and this PT represents the total pressure at time T exerted by all the gaseous components, and here the gaseous components are A, capital A, B and C. So the PT total pressure can be written as the sum of partial vapor pressure of the component A plus partial pressure of the component B plus partial pressure of the component C. Okay. After that, now I am going to calculate the value of Pi and the rate constant. So, now I am going to calculate the value of PT and rate constant. Okay. Calculation of P total and rate constant for a gaseous first order reaction. So first we assume that if X atmosphere be the decrease in the pressure of A and the 1 mole of B and 1 mole of C will be formed during the course of the reaction, and similarly there is an increase in the pressure of B and C will be observed by X atmosphere each. Okay. So for this reaction, that is the A, on reacting it give the product B and C at T is equal to 0. What is the pressure of PA? Pressure of B and pressure of C. Okay. At T is equal to 0, what is the value of PA? The value of PA is Pi, that is the pressure, initial pressure, and the initial pressure is only due to the component A, and the component B and C are not formed at T is equal to 0. So it is 0 atmosphere. This is Pi. Okay. At time T, what happens? There is a decrease in Pi by X atmosphere will be observed. That is, at time T, the pressure is due to the component A is Pi initial pressure minus X. Okay. And similarly, there is an increase in the pressure of the component B and C. Each by X atmosphere will be observed. That is X atmosphere, and here also X atmosphere. Okay. So at time T, the total pressure at time T is equal to what? This is the sum of Pi minus X, X and X. That is Pi minus X plus X and plus X. The one term is cancelled out. That is Pi plus X. Okay. The PT is equal to Pi plus X. So, and what is the value of X? X atmosphere is equal to, that is equal to PT minus Pi. Okay. Now, the pressure of the reactant, the pressure of the reactant A at time T will be what? At time T, what is the pressure due to the component A? That is Pi minus X. At time T, the pressure due to component A is Pi minus X. That is equal to Pa, pressure of the component A at time T. So, what is the value of X? The X is equal to Pt minus Pi. So, we can substitute this value, that is a Pi minus Pt plus Pi. Okay. That is 2 Pi minus Pt. That is equal to Pa. The pressure of the component A at time T is equal to 2 Pi minus Pt. So, this value can be substituted in the integrated rate equation containing the partial vapor pressure of the component A at time T. That is, the K is equal to 2.303 by K log Pi by Pa. Initially, I had also written this, that is the integrated rate equation, and in the integrated rate equation, when we are considering the pressure of the reactant and product, then the concentration term is directly proportional to pressure. So, this is the pressure, initial pressure, and the initial pressure is only due to the component A initially at T is equal to 0, and this PA is the pressure of the reactant A, final pressure of the reactant A at time T. So at this place we can substitute the value of PA, that is 2 Pi minus PT, and after that we got that is 2.303 by T log Pi by 2 Pi minus PT. Okay, so in this way, when we are knowing the value of initial pressure and the total pressure for a gaseous first order reaction and the time for this reaction, we can calculate the value of the rate constant for a gaseous first order reaction. Okay students, the first, here we are calculating the value of rate constant for a typical first order gaseous reaction. This is the gaseous reaction A, on reacting it gives the product B and C. So the integrated rate equation for the gaseous first order reaction can be written as the, here T, the K is equal to 2.303 by T log Pi by Pa. Okay, this Pi is the initial pressure of the component A and Pa is the pressure of the component A at time T. If PT will be the total pressure due to the all the components, means the total pressure which is exerted by the gaseous mixture of A, B and C. So the PT is equal to the partial vapor pressure of A, Pa plus Pb plus Pc. So if we assume that, now I am going to calculate the value of PT and the rate constant. So if we assume that the X atmosphere will be the decrease in the pressure of A at time T, and 1 mole of B and 1 mole of C will be formed, and consequently there will be an increase in the pressure of B and C, same by 1 atmosphere. So in this case at T is equal to 0, the pressure of A is Pi atmosphere, okay, and the pressure of B and C will be 0 atmosphere because it does not form at T is equal to 0. So, but as the reaction is proceeding at time T, if we assume that the X atmosphere pressure will be decrease of A, so the pressure of Pa at time T is equal to Pi minus X atmosphere. Similarly, the X atmosphere increase in the pressure of B and X atmosphere increase in the pressure of C will also be observed. So at time T, the pressure of B will become X atmosphere and the pressure of C will become X atmosphere. Okay. So at time T, the total pressure PT is equal to what? That is this pressure of component A, pressure of the component B and pressure of the component C, that is Pi minus X plus X and X. So after that we got the P total is equal to Pi plus X and the X is equal to PT minus Pi. Okay. Now the pressure of A at time T will be what? That is Pa, and the Pa is at time T, the pressure of A is Pi minus X. So Pi minus X, we can substitute the value of X, that is Pt minus Pi. So after that we got the value of Pa, the pressure of A at time T, that is 2 Pi minus Pt, and after that I substitute this value of Pa in the integrated rate equation for the first order reaction. After that, the next topic is the half-life of a reaction. The half-life period of a reaction is defined as the time during which the concentration of the reactant is reduced to half of the initial concentration of the reactant. Okay, the half-life period of the reaction can also be defined as the time required for the completion of half of the reaction. So the half-life of a reaction is the time required for the completion of half of the reaction. Time required for the completion of half of the reaction, or we can say that the time during which the concentration of reactant is reduced to half of the initial concentration of the reactant. Okay? The half-life of a reaction is defined as the time required for the completion of half of the reaction, or we can say that the time during which the concentration of the reactant is reduced to half of the initial concentration of the reactant. And the half-life of a reaction is represented as T half 1/2 or T 0.5. This is the representation of the half-life of a reaction. Now we move to derive the equation for the half-life period for a zero order reaction. Okay, the half-life of a zero order reaction. Half-life of a zero order reaction. Okay, then what is the integrated rate equation for the zero order reaction, which we have already derived in the previous class? That is the R is equal to R naught minus KT. Okay, this is the integrated rate equation for the zero order reaction. Here R is the final concentration of the reactant, R naught is the initial concentration of the reactant, K is the rate constant, and T is the time. Okay, at T is equal to T half, then what is the final concentration of the reactant? The final concentration of the reactant is reduced to half of the initial concentration. That is, the final concentration is equal to half of the initial concentration, that is R naught by 2. Now I am going to substitute this value in this equation 1. After that we got, that is R naught by 2 is equal to R naught minus KT half. Okay, then KT half is equal to what? This is equal to R naught minus R naught by 2. Okay, after solving this, the KT half is equal to R naught by 2, and T half, the half-life period for a zero order reaction is what? It is equal to initial concentration divided by 2K. Okay, so with the help of this equation we can calculate the half-life period for a zero order reaction by knowing the R naught and the value of the rate constant. So from this equation it is clear that the T half for a zero order reaction is directly proportional to what? Directly proportional to the concentration of the reactant. That is, the T half is directly proportional to the concentration of the reactant. So when we are going to draw a plot between the half-life period and the concentration for a zero order reaction, then a straight line is found. Okay, and the slope of the line is equal to 1 by 2K. So from this case it is clear that the half-life period for a zero order reaction is directly proportional to the concentration of the reactant. After that, the next is the half-life of a first order reaction. So we know the integrated rate equation for the first order reaction, that is the K is equal to 2.303 by T log initial concentration of the reactant divided by final concentration. Okay, so the T is equal to 2.303 by K log initial concentration divided by final concentration. Okay, this is the integrated rate equation for the first order reaction. At T is equal to T half, then what is the final concentration? The final concentration is half of the initial concentration, that is R naught by 2. Now I am going to substitute this value in this equation 1. Then after that we got that is the T becomes T half is equal to 2.303 K log R naught divided R naught by 2. This is cancelled out and we got that is the T half is equal to 2.303 K log 2, and the value of log 2 is equal to 0.301. Okay, 0.301. So now I am going to substitute the value of log 2, that is 2.303 K into 0.301. After solving this we got 0.693 by K, that is the T half for a first order reaction is equal to 0.693 by K. Okay students, so in this equation you see that this equation does not carry any concentration term. It means the half-life period for a first order reaction is independent on the concentration of the reactant. It means the T half for a first order reaction is a constant value, and by drawing a plot between T half and the concentration, the line is obtained like that, which shows that with changes in the concentration, the T half does not change. It means the T half become independent on the concentration of the reactant, and the T half is a constant value. It does not changes by changing the concentration. Hence, the half-life of a reaction with nth order can be calculated as T half of reaction with nth order. We can calculate the half-life period for a reaction with nth order by using this expression, that is the T half is equal to 1 by initial concentration power n minus 1. Here n is the order of the reaction. So for zero order, what is the value of n? That is 0. It means the T half here is directly proportional. The T half is directly proportional to what? Initial concentration of the reactant, because it is a 0, 0 minus 1 means minus 1, and here R naught is raised to up and it is directly proportional to the half-life period for a zero order reaction. Similarly for first order reaction, the T half is directly proportional to what? It is directly proportional to 1. It is a constant term. It does not depend upon the initial concentration of the reactant. For the second order reaction, the T half is directly proportional to 1 by initial concentration of the reactant. And for the third order reaction, the T half is directly proportional to 1 by initial concentration of the reactant raised to power 2. So by using this expression, we can derive a relation between the T half and the initial concentration of the reactant for a reaction with nth order. So the plots of T half versus concentration. Okay. With the help of plot, the plots of T half versus concentration. First for the zero order reaction, here T half and concentration. For zero order reaction, it is directly proportional to the concentration of the reactant. For first order reaction, on the y-axis taken the T half and on this axis concentration. So for the first order reaction, the T half is independent on the concentration of the reactant. So we obtain this line, and this line shows that the T half does not depend upon the concentration of the reactant and it is a constant value. This is for the first order reaction. Okay. Second, for the second order reaction, here T half and here 1 by concentration. Okay. We also get a straight line. Similarly, for third order reaction, this is for the third order reaction. Here we take the T half and here 1 by concentration square. Okay, and we get a straight line. So in this way, with the help of plot, we can easily recognize the order of the reaction. When the reaction is when the plot is a straight line between T half versus concentration, then this is a zero order reaction. When the line is obtained like this, showing the T half is independent on the concentration of the reactant, this is for the first order reaction. And when the plot between T half and 1 by concentration is a straight line, it is a second order. And when the plot between T half versus 1 by concentration square is a straight line, then this is for the third order reaction. In addition to calculate the T half, we can calculate the time required for the completion of different fraction of the reaction. Now I am going to calculate the time required for the completion of 1 by third of the reaction. That is the T 1 by 3 is equal to 2.303 by K log A, initial concentration, divided by what is the final concentration, that is A minus A by 3. Okay. After solving this, we got that is 2.303 K log 3 by 2. Okay. And solving this, after calculating this, we got the result, that is 0.406 by K. Okay. So by using this equation, we can calculate the time required for the completion of 1 by third of the reaction. Similarly, the time required for the different fraction of the reaction can be calculated as, that is the time required for the completion of 75% of the reaction, that is the 3 by 4, or T 75% is equal to 1.386 by K. Okay, 1.386 by K. Similarly, for 60%, 0.66 or 0.6 or 60% is equal to, that is equal to 0.9165 by K. Similarly, for 90%, 0.9 or T 90% is equal to 2.303 by K. Similarly, for completion of 99.9%, the time required for the completion of 99.9% is equal to 6.909 by K. So in this way, we can calculate the time required for the completion of different fraction of the reaction. For 1 by third, the value is the T 1 by 3 is equal to 0.406 by K. Similarly, for 75% completion is equal to 1.386 by K. For 60% completion is equal to 0.916 by 65 by K. For 90% completion, this is equal to 2.303 by K. And for 99.9% completion, this is equal to 6.909 by K. So by using this equation, in general, we can calculate the time required for the completion of different fraction of the reaction, that is for the completion of 1 by nth fraction. Okay, that is the T 1 by n is equal to 2.303 K log R naught, initial concentration, divided by what is the final? The final is R naught minus R naught by n. Okay, for calculating the time required for the completion of 1 by nth fraction of the reaction. And after this, the 2.303 by K log 1 by the R naught are cancelled out, that is 1 minus 1 by n. So after that, we got 2.303 by K log n divided n minus 1. Okay. So in this way, by using this expression, this is general expression, and by using this expression we can calculate the time required for the completion of 1 by nth of the chemical reaction. So by using this general expression we can calculate the time which is required for the completion of 1 by nth fraction of a chemical reaction. So students, that's all for today. Till then, be safe and enjoy your holidays.